For a 400 amp service, the minimum allowable wire size for the feeder is number 1 American wire gauge. The National Electrical Code states that paralleled conductors for motor circuits must be of the same size and length. Given that the load is split into 2 drives, the current through each drive will be approximately 200 amps. Now let's use Ohm's law to verify this assumption. Ohm's law dictates that voltage equals current times resistance. Therefore, the voltage drop in the wire can be calculated using the formula volts equals amps times ohms. For number 1 American wire gauge copper wire, the resistance is approximately 0.5 ohms per foot. Thus, volts equals 200 amps times 0.5 ohms per foot. Considering a reasonable distance between the disconnects and the drives, the resulting voltage drop will likely be negligible. The choice of number 1 American wire gauge conductors for paralleling to each input terminal of the drives is therefore sufficient. Proper conductor sizing is essential for safe and efficient operation of electrical systems. Undersized conductors can overheat, leading to insulation damage, fire hazards, and voltage drop issues that affect equipment performance. Oversized conductors, while safer, increase material costs and can be difficult to terminate properly, so it is vital to select a conductor size that meets the requirements of the National Electrical Code in the specific application. Several factors influence the selection of the appropriate conductor size. Firstly, ampacity, which is the maximum current a conductor can carry continuously without exceeding its temperature rating. The National Electrical Code provides ampacity tables based on conductor material, insulation type, and installation conditions. Secondly, voltage drop, which is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to no more than 5% for feeders and branch circuits. Thirdly, ambient temperature, which affects the ampacity of conductors. Higher ambient temperatures reduce the ability of conductors to dissipate heat, requiring a reduction in ampacity. The National Electrical Code provides correction factors for adjusting ampacity based on ambient temperature. Fourthly, number of conductors in a raceway or cable. When multiple current-carrying conductors are installed in close proximity, the heat dissipation is reduced, requiring a reduction in ampacity. The National Electrical Code provides adjustment factors for directing ampacity based on the number of conductors. Fifthly, conductor material. Copper and aluminum are the most common conductor materials. Copper has a higher conductivity than aluminum, meaning it can carry more current for a given size. However, aluminum is less expensive and lighter than copper. Sixthly, insulation type. The type of insulation affects the temperature rating of a conductor. Common insulation types include THHN, THWN, and XHHW. Each insulation type has a different maximum operating temperature. Seventhly, installation method. The way a conductor is installed affects its ability to dissipate heat. Conductors installed in free air can dissipate heat more easily than conductors installed in conduit or cable trays. Eighthly, load characteristics. The type of load being served affects the conductor size requirements. Motor loads, for example, require larger conductors than lighting loads due to their inrush current during startup. Ninthly, future expansion. It's important to consider future load growth when sizing conductors. Installing larger conductors than currently needed can provide capacity for future expansion without the need to replace the conductors later. Lastly, National Electrical Code requirements. The National Electrical Code provides detailed requirements for conductor sizing, including ampacity, voltage drop, and overcurrent protection. It's essential to comply with all applicable National Electrical Code requirements to ensure a safe and code-compliant installation. For a single motor, the National Electrical Code Section 430.22 and 430.52 provide the guidelines for conductor sizing and overcurrent protection. These sections account for the motor's full load current, starting current, and duty cycle. Conductors supplying a single motor must have an ampacity of not less than 125% of the motor's full load current rating. This ensures that the conductors can handle the motor's continuous load without overheating. The motor's overcurrent protection device, such as a circuit breaker or fuses, must be sized to protect the motor from overloads and short circuits. The National Electrical Code Section 430.52 specifies the maximum allowable size of the overcurrent protection device based on the motor's type, horsepower, and voltage. For multiple motors on a single feeder, the National Electrical Code Section 430.24 provides the rules for conductor sizing. The feeder conductors must have an ampacity of not less than 125% of the full load current rating of the largest motor, plus the sum of the full load current ratings of all other motors in the group. This ensures that the feeder conductors can handle the combined load of all the motors without overheating. The overcurrent protection device for the feeder must be sized to protect the feeder conductors and the motors. The National Electrical Code Section 430.62 specifies the maximum allowable size of the overcurrent protection device based on the feeder's ampacity and the motor's characteristics. When paralleling conductors, which means using two or more conductors connected in parallel to increase ampacity, the National Electrical Code Section 310.10h provides the requirements. Firstly, all parallel conductors must be of the same length, conductor material, size, insulation type, and be terminated in the same manner. This ensures that the current is evenly distributed among the parallel conductors. Secondly, the minimum size for parallel conductors is number 1 over American wire gauge, except as permitted in specific circumstances. This limits the use of smaller conductors in parallel to reduce the risk of uneven current distribution. Thirdly, each parallel conductor must be protected by an individual overcurrent protection device. This provides protection against overloads and short circuits in each conductor. Fourthly, the overcurrent protection device must be sized to protect the conductor's ampacity. This ensures that the conductors are protected from overheating. Variable frequency drives are electronic devices used to control the speed of alternating current motors. Variable frequency drives provide several benefits, including energy savings, improved process control, and reduced mechanical stress on motors and driven equipment. Variable frequency drives work by converting incoming alternating current power to direct current power, and then converting the direct current power back to alternating current power at a different frequency. By varying the frequency of the alternating current power, the speed of the motor can be controlled. Variable frequency drives also allow for adjustable voltage, current limits, and ramp up and ramp down times. When installing variable frequency drives, it's important to follow the manufacturer's recommendations for conductor sizing, overcurrent protection, and grounding. Variable frequency drives can generate harmonic currents, which can cause overheating of conductors and equipment. To mitigate the effects of harmonics, it's recommended to use appropriately sized conductors and install harmonic filters. The National Electrical Code provides specific requirements for grounding variable frequency drives. Proper grounding is essential for safety and to minimize the risk of electrical noise and interference. When replacing existing motors with variable frequency drives, it's important to verify that the existing conductors are adequately sized for the variable frequency drive's output current. Variable frequency drives can produce higher peak currents than traditional motor starters, so it may be necessary to upgrade the conductors. Proper labeling of conductors and equipment is essential for safety and to facilitate maintenance and troubleshooting. All conductors should be clearly labeled with their size, voltage, and function. Equipment, such as disconnect switches and circuit breakers, should be labeled with their ratings and the equipment they serve. Regular inspections and maintenance of electrical systems are essential to ensure their safe and reliable operation. Inspections should include checking conductors for signs of damage, such as overheating or insulation breakdown. Maintenance should include tightening connections, cleaning equipment, and testing overcurrent protection devices. The National Electrical Code is a comprehensive set of standards and guidelines for the safe installation and maintenance of electrical systems. The National Electrical Code is updated every 3 years to reflect changes in technology and best practices. Compliance with the National Electrical Code is essential for ensuring the safety of people and property. State and local jurisdictions may adopt the National Electrical Code as law, making compliance mandatory. Electrical codes and standards are essential for ensuring the safe and reliable operation of electrical systems. By following the requirements of the National Electrical Code and other applicable standards, electrical professionals can minimize the risk of electrical hazards and protect people and property from harm. Proper conductor sizing, overcurrent protection, grounding, and maintenance are all critical aspects of electrical safety. Continuous education and training are essential for electrical professionals to stay up to date on the latest codes, standards, and best practices. Technology plays a crucial role in modern electrical systems, from smart meters to energy-efficient lighting. Embracing new technologies can improve the performance, reliability, and safety of electrical systems. However, it's important to understand the potential risks associated with new technologies and to implement appropriate safeguards. Collaboration among electrical professionals, manufacturers, and regulators is essential for developing and implementing safe and effective electrical systems. By working together, we can create a safer and more sustainable future for all. For the specific scenario of installing a new 400 amp single-phase service to a small water pumping station where the service feeds to 200 amp fused disconnects protected by 175 amp breakers, and from the load side of the disconnects, 2 variable frequency drives are fed, and given the desire to run 2 conductors in parallel to each but due to difficulty fitting a single larger conductor, the question of whether to use number 1 American wire gauge or number 2 American wire gauge should be addressed with a comprehensive understanding of the National Electrical Code and the principles of electrical engineering. Firstly, verify the National Electrical Code compliance. The National Electrical Code dictates the standards for electrical installations, including conductor sizing and paralleling. It is essential to ensure the installation adheres to these standards for safety and code compliance. Secondly, analyze the load requirements. Each variable frequency drive is intended to handle approximately 200 amps. Therefore, the parallel conductors must be capable of carrying at least this amount of current safely. Thirdly, assess the ampacity of conductors. Number 1 American wire gauge and number 2 American wire gauge conductors have different ampacities. Consult the National Electrical Code ampacity tables to determine the allowable ampacity for each conductor size, considering the conductor's insulation type, installation method, and ambient temperature. Fourthly, calculate the voltage drop. Voltage drop is the reduction in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to no more than 5% for feeders and branch circuits. Use Ohm's law, volts equals amps times resistance, to calculate the voltage drop for both number 1 American wire gauge and number 2 American wire gauge conductors. Consider the length of the conductors and their resistance per unit length. Fifthly, consider the paralleling requirements. When paralleling conductors, the National Electrical Code requires that they be of the same material, size, length, and insulation type. Also, the overcurrent protection must be coordinated to protect the conductors. Sixthly, evaluate the terminal capacity. The original problem statement mentioned difficulty fitting a single larger conductor into the variable frequency drive input terminals. Ensure that the chosen parallel conductors can be terminated properly in the terminals. Seventhly, account for future expansion. Consider whether the water pumping station's load is likely to increase in the future. If so, it may be prudent to install slightly larger conductors to accommodate future growth. Eighthly, consult with a qualified electrical engineer. For complex electrical installations, it is always recommended to consult with a qualified electrical engineer. An engineer can perform detailed calculations and provide recommendations based on the specific requirements of the installation. Ninthly, consider the cost. Number 1 American wire gauge conductors are typically more expensive than number 2 American wire gauge conductors. Factor in the cost of the conductors, as well as the cost of installation and any necessary hardware, when making the decision. Lastly, document the design. Keep a record of all calculations, assumptions, and decisions made during the design process. This documentation will be helpful for future maintenance, troubleshooting, and modifications.